ChatGPT is amazing, and so are all the other generative AI-powered chatbots like Bing and Bard. They can answer detailed questions on expert knowledge domains for you. They can summarize text. They can translate text from one language to another or one style to another. They can write poetry and prose. They can solve problems. They can chat with you and give you life advice. They're amazing, and nobody saw this breakthrough coming. I think it's taken the world by storm, including the AI and natural language processing community and the researchers who made that bot. Nobody expected those large language models that power those systems to be this good. At the same time, they have problems that nobody knows how to overcome. So they tend to make things up. They call them hallucinations. They will often say things sometimes that seem to violate common sense, things that no human being would ever say. If you haven't interacted with one of these bots, you should do it. Try to get the best out of it, and then see if you can confuse it, see if you can get it to say things that don't make any sense. Look at where the edges of what it can do are. The big question, the one that I want to address here is, what kind of system is this that does both of those things, that can be on the one hand so amazing and on the other hand make such elementary mistakes? How does that happen? That's what I want to address here. I think that understanding this technology is imperative for everybody who uses the technology and wants to understand how to use it and what to expect from it. And also, it's really useful to know how they work when you're trying to evaluate claims that are being made right now about artificial general intelligence, the coming robot apocalypse, or even just what the impact is going to be on jobs in the future by these AI systems. So I believe that you can you can learn how these things work without needing to have a computer science background, without needing to have a lot of mathematical sophistication. So my name is Sam Scott. I'm a professor at Mohawk College, where I develop and teach AI and machine learning courses and programs. And the goal of this video and the ones coming after it is to explain in simple terms to civilians how these systems work and how they do what they do. So in this video, I want to focus on the task. So before I take you inside the neural networks that power ChatGPT in particular, and the rest of the large language model chatbots, let's talk about what exactly is it that they're trained to do. What is the problem that they're solving? And you might say, "Oh, that's easy. They answer questions, or they solve problems, or they look stuff up for me." No, not really. I mean, that's how you can use them. But I'm talking about the core task that they are trained to solve. So that's what we're going to look at in this video. And then in the next video, the idea is that we'll go inside and see how they accomplish this core task. So the core task of ChatGPT and all of the bots that use this generative AI is the following: given a text prompt, so the thing that you typed, predict the next natural language token that should come after what you typed. A natural language token is a fancy way of saying a word, but it's a bit more than a word. It can be a part of a word, or it could be a punctuation mark. What item needs to come next or ought to come next after what you typed? That's it. That is its core task. And it's trained to do that based on a massive amount of English and other language text that comes from the internet and from a bunch of other sources as well. So that's what it's trying to do. It's a large language model. All of these generative AI text bots are built on something called a large language model, and they're powered by a deep artificial neural network architecture called a transformer. We're going to leave aside the neural network architecture right now. We'll come back to it in a future video. But right now, let's talk about what does it mean to be a large language model? And actually, for that matter, what does it mean to be a language model? What does a language model do? Okay, so a language model is a probability distribution for sequences of words or tokens in a natural language. So what that means is, in simple terms, is if you have two strings of words, here's two, for example, it's my day in the sun versus the same words but scrambled, my, it's, Sunday, the, in. So we would probably say the first one is grammatical English, and the second one is English words, but it's gobbledygook. It's not grammatical. You can't get any meaning out of it. A probability distribution doesn't look at it in such black and white terms. It looks at it in sort of shades of gray, probabilities. So a large language model or a language model might say, yeah, it might give a score of 90% to the first one, meaning, yeah, that's you could interpret it a number of ways. It might mean, yeah, that's probably in the language, or it might mean, yeah, I think that's something that a speaker of English would be pretty likely to say. Or this is a pretty good example of an English sentence. So rather than just saying it's grammatical, it'll give it that score. The one on the right will have a very low score, like maybe 0.1%. Again, not really meaning it's not grammatical, but meaning that's really, really unlikely that anybody speaking this language would say those words in that order. You can, once you've got a probability distribution that you can feed words into and get scores out of, you can also, with a slight tweak, you can do what are called conditional probabilities. So that means, for example, if I give you, it's my day in the, what is the probability that the word sun will come next? And since that's a noun and it fits the sentence, and it's something that people say sometimes, it's sort of an idiom that means, it's my turn to shine, or my turn in the spotlight, or good things have been happening to me lately, or something like that. It might assign a high probability to that. It might say, yeah, 53%, I think, that it's likely that the next word is sun. Whereas if the context is different, if the conditions are different, would you like to purchase the... Now, would you like to purchase the sun is a perfectly grammatical sentence with a well-defined meaning, but it's not something that people would be very likely to say. So a large language model would probably give that a low percentage score and a higher percentage to other words, like, would you like to purchase the car, or something like that. Okay, so a language model can produce these conditional probabilities given a context for any word in its vocabulary. So any word that it knows about, it can tell you what it thinks the probability is that that word should come next after what you typed. Notice, by the way, that in this case, the low probability doesn't come from the grammar, right? So the language model mixes together grammar and meaning and appropriate usage to come up, and mixes them all together to come up with one score, which is, it's not the way we tend to think about it. It's not the way linguists, people who study a language, think about it, but it works really well for what we're trying to do. So when a language model comes out with a probability, it's not really a statement just about the grammar or a statement just about the meaning. It's a statement of sort of just in general how good that sentence is, or that string of words is. Okay, so how do we turn this into something like ChatGPT? Well, ChatGPT works one token at a time. So if I type the prompt into ChatGPT or a large language model of any kind, how are you today? It will look at that string of tokens and ask itself what word is most likely to come next. And it might decide that I is the most likely word to come next. So it's the first word it'll produce in response. Then it does it again, but this time it sticks the word that it produced onto the prompt. So now the context is, how are you today, I? And it might decide that apostrophe M, as in I'm, is the next most likely thing to come out. And it keeps going and building it that way. So each time it runs the entire original prompt through the model, plus the words that it has chosen so far. And at each step, it's asking, what should the next word be? What should the next word be? What should the next word be? And it's estimating a probability of all the different words that it knows about to make that decision, to make that call. So that might continue like this. I'm doing well, thanks for, et cetera, et cetera, et cetera. At some point, it stops. There are special sort of stop tokens built in. So when it predicts a stop token, it'll end. Sometimes it'll be cut off if the system that is controlling ChatGPT or the language model decides that it's produced enough tokens, or that it's produced a special something that looks like an ending sequence. So there's an extra little problem about when do you stop. But that's the core of it, is one word at a time generated using probabilities. And if you don't believe me, you can go here, platform.openai.com/playground, and try this little activity here. In fact, I'll click on it now and we'll go there. You may find that you have to create an account and log in. It's okay. It's free to do so. And there's a couple things you can do. There's blocked by my image here, but you should make sure it's on mode complete. And if you scroll down to the bottom, you should change show probabilities to full spectrum like that. Now, this is not a chatbot. This is a very raw implementation of a large language model. This is a site for developers. So you can type something and then it will it'll do its completion job of figuring out what the next words should be. So if I say, how are you today? And hit submit, it will generate a bunch of text for me. And if I click on one of the words, it's showing me here what it thought were the most likely things to come next at that point when it was generating. And you can see here, it thought that a period would be the most appropriate thing to put here, as in, I'm doing well, thank you, period. But then 4, as in thank you for asking or whatever, was the next one. And that's the one that it happened to pick. So it tends to usually, if you click on these words, you'll see it usually picks the top choice, but occasionally it might pick a different choice. So here, how, instead of how about, it went with how are. Okay, so that is literally what it's doing. It's just going through, and it's at each stage, it's choosing the probability for the next word. So what I want to do now is I want to talk about, okay, how could you produce a language model? I don't want to talk about the exact implementation of ChatGPT. We'll talk about that later on. I just want to kind of, as an intuition, I want to imagine a very simplistic, simple way that we could create a language model and sort of explore how well that language model does, and how we would go from there to ChatGPT. And I think it'll be valuable. So stick with me here. I think it'll be helpful. I wrote a little bit of code, because I'm that kind of nerd, to implement what I call a tiny language model, or TLM for short. So a very small language model. And I did it in different versions. So in the first version, it's as simple as it could possibly be. I got myself a data set, about 62 megabytes of text, which, as far as I can tell, is about 10,000 times smaller than the amount of text that was used to train GPT-3, and let alone GPT 3.5 and GPT-4 and so on. And I have my system go through all of that text and count the occurrences of the words. So here I've got in this table here the top 5 tokens, sorry, I should say, that appeared. So the top one was the period, appeared 135,000 times in the text, then the word I, then the word the, and so on. And I can turn that into a frequency, which I can then use as a probability estimate. So here, out of when I add up all the tokens that were in this big, huge chunk of text, if 135,000 of them were the period, well, that's a frequency of 6.7%. I just divide one by the other. So that represents 6.7% of all the tokens. The word I represents 3.7, and so on and so on. And then what I can do is I can just begin to generate text. I can't take into account any context at this point, but I can generate text just by selecting words at random based on these frequencies. And I would do that with a technique called roulette selection, which we don't have to go into the details of, but you can kind of imagine it like this. If I was going to select from these 5 words using roulette selection, I would create a system where you can imagine it as a roulette wheel that's going to spin, and this arrow is going to point to something. And the slices on the roulette wheel are proportional in size to the probability or the frequency of that word. So when I spin this, the most likely thing to come up is the dot, and the least likely is the word that. Now imagine that, but with all, I think this set had 28,000 words in its vocabulary. So there were 28,000 different unique tokens of text that I found in that 62 megabytes, and I counted all of them. So the roulette wheel for that would be much, much smaller, skinnier little pies. And then I spin it, and I just spin it repeatedly, and I output the words that come up. Okay, so that's a really, really simple, tiny language model that has been formed by looking at real text. So when you use it, again, this is TLM1, my first tiny language model. This is the kind of thing it outputs. It's not very good. Those optimism, I, it, doubt, getting, would we, and, question mark, and so on and so on. It's gobbledygook, as you might expect. But the generation does respect the frequencies that those tokens appeared in the language. So the word the is going to be a lot more common than the word optimism in the output. What I do is how I decide where to stop is I go for about 30 tokens. And then once 30 tokens have come out, I keep generating until I find a punctuation, like a period or a question mark, and then I stop. Okay, so that's TLM1. It's lousy. Here's TLM2. TLM2, Tiny Language Model 2, doesn't just count words, it counts what are called bigrams. So pairs of words or pairs of tokens. So see, it comes up with counts like this. The same appeared 1,100 times in the text. The other appeared 1,000 times. The time appeared 854 times, and so on. And we can use these counts now. We can use them to generate prediction probabilities for words that come next. So if the previous word was the word the, then I look up all of the bigrams that start with the word the. I look up their counts, and I find their frequencies. This is the frequency of of all the bigrams that started with the word the same came up 1.7% of the time. And then I take the top 10 or 15. I think I went with 15, and I do a roulette wheel selection on that. So if you type hello, it'll look for all the bigrams hello that start with hello and then have something else. And then it will do a selection based on that. And if it chooses the word there, as in hello there, then it will now look at the bigrams that start with the word there, and it'll choose the next word and so on. Okay, so when you do that, so here's an example of it actually running. I just put in the prompt the word I. So the context that it's using to begin its generation is the word I. And it comes up with have been, to be, an interesting, the one of the only, the same time with them. I mean, it's gobbledygook again, but it's better than the previous one. It's a little bit more grammatical. It almost seems like maybe we're beginning to get actual sentences and meaning in there. It's sort of like when you play that game on your phone where you just type in a prompt and then you hit next word, the next predicted word over and over and over again. These games you see them on social media every now and then. It's very similar to that. Those are also running language models. Your phone is running a language model, and that's how it predicts what should come next. Same thing with Gmail and Google Docs. When you start to type, they will often predict stuff for you. It's based on a language model, not much more sophisticated than this, much less sophisticated than ChatGPT, but same basic idea. Here's another example where it almost seemed to make sense. So I typed in the prompt hello. So that's two tokens, hello and an exclamation mark. And so the context that it starts with is just the exclamation mark, and it comes up with this, the whole lot, the first year, the same problem. In the last 2 years ago, the same thing. It sort of sounds like somebody who's a little bit upset about something and is trying to get their point across, but is kind of sputtering. So you can almost begin to read meaning into some of these things, some of these sentences, even though we know that there's no meaning in there. It's just generated based on frequencies. The only thing that we know is that, if you look at each pair, they should make sense. The whole lot, the first year, because it's doing it in terms of bigrams. Those are the parts of it that make sense, but the whole thing, the whole sort of gestalt, doesn't make a lot of sense. Okay, then I can keep it going. So I did it with trigrams. That's 3-word counts. Here's a prompt, tell me something interesting. So the context here is interesting, period. And it says, oh, I know that's a big change. There is a little bit more. So now we're getting actual sentences out of the thing, and then stuff that doesn't make sense again. It doesn't seem to be that related to what I asked it to do, but it's more grammatical. I went to 3-word context. So 4grams, quadgrams, I guess. So we're looking at sequences of 4 words. So we take a sequence of 3 words and we try to predict the next one after that. So now the context is something interesting dot. And it's going to predict that the next word is one. And it says one possible solution is quite a radical one. Say if each household in Britain was only allowed 1 car. It sounds pretty good. I mean, it's off topic of what I asked it to do, but the text is sounding better and better and better. Okay. So hopefully that gives you a little bit of a sense of how this could possibly work, like how you can actually use existing text to generate a system that's able to come up with probabilities and use those probabilities to create, text that starts to seem more and more lucid. The question is, how do we get from these tiny models to the actual large language models that are doing all those amazing things? So first point is large language models are massively, massively scaled up. So GPT-3, instead of 62 megabytes, used over half a terabyte, 570 gigabytes of text. That's half a trillion tokens of training text. It cost $12 million of computer time and energy costs to train the thing. And when it does predictions, it doesn't just take the last 2 or 3 or 4 words. It can take up to 2,000 words of context. So you can write a whole short story to it. You can give it a really, really detailed set of instructions. And it is somehow able to take all of that into account when it's predicting the next word. So it can look at the previous 2,000 words and use all of that information to come up with a decent next word. GPT-4, which is the one that's out now and is probably going to be the ultimate one for a while, they don't tell us what they trained on or what it cost. We have very good reason to believe that it's even bigger than GPT-3 and even more expensive. And this one comes in 2 varieties. It can take, the first variety takes 8,000 words of context. the biggest one takes 32,000 words of context. So you can put a whole short novel in there, or the first 2 chapters of a novel, and ask it to continue the novel, and it will be able to take into account all of that context. But here's the problem. So the tiny language model, the one that I showed you where we just count things, it just doesn't scale up. ChatGPT could not be using that approach. One reason is because of storage. My texts, my 62 megabytes of text, which is a really small data set, had 28,000 different unique tokens in it, 28,000 words. When we look at the bigrams, the 2-word sequences, there's 300,000 of those. There's almost 900,000 trigrams, over 1 million sequences of 4 words. How about 2,048 grams? How many sequences of 2,000 words would there be in any given corpus? A lot. So the storage requirements here are going to get out of hand pretty quickly if you're trying to take more than just a few words of text into account. But the bigger problem actually is not the storage problem; it's a problem of sparsity, right? So the longer the sequence of words, the rarer it's going to be. So in my set of text data, the big green, that 3-word sequence, only had 1 occurrence. I think it came in a sentence about the big green trash can or something like that. There was only 1 occurrence of that. So that means that my model, if it's using 3 words of context, is only going to have 1 choice if it sees that in the text. If it sees the big green, it's only going to have 1 choice that it's going to use for the next word. Furthermore, the big red and the big blue, they're not in my corpus at all. So if it sees that, it's going to be stuck. Now, think about ChatGPT and think about like a sequence of 2,000 words, maybe a few paragraphs of a novel or a few pages of a novel. How likely is it that that's ever going to come up again more than 1 time? Extremely unlikely. So we actually have, when we're trying to take into account large bits of context, we have a sparsity problem. There just aren't enough examples to use the counting approach that I used in the tiny language model. So what that means is large language models have to generalize. They have to be able to say, okay, I've never seen that string of 2,000 words before, but I've seen things that were similar in meaning or similar somehow in some way to that string of 2,000 words. And maybe I can come up with an estimate for a probability, for probabilities for the next word that I should generate based on stuff that I've seen that has some similarities to this text. And that's essentially what they do. The way they do it is complicated and difficult to understand, but I'm going to try and break it down in the next video. But what they're doing is they're generalizing. So the next video is going to be a journey through a large language model, where we're going to look at this architecture that you see in front of you here, and we're going to look at the journey of a word through this architecture and see what happens to it, how it gets processed. And again, I'm going to try and do it in a way that you shouldn't have to be a computer scientist or a mathematician to be able to understand it. My hope is that this might have helped open some eyes about exactly what the task is behind these language models. And now that you know that they are just kind of guessing at the probability of the next word, it might make it clearer how the same system can produce really good answers to questions on the one hand, but then also make really basic mistakes on the other hand. It's not actually doing any reasoning in there. Well, that's controversial. I'll talk about that in the next video. Some people think that maybe it is, or that reasoning is an emergent property of this system. But it is, what we can say for sure that I think is uncontroversial is that we're generating 1 word of text at a time. And that doesn't seem like, that's not the way that we feel like we talk. And linguists and cognitive psychologists think that we talk. It seems like when we talk, we have a thought in mind, and then we try to express it in language. Whereas when ChatGPT talks, first you have to feed in a bit of language to it, and then it just starts kind of trying to think what's the plausible next word and the next word and the next word and the next word. That doesn't feel like the way that we talk. And don't let anybody tell you that that is the way you talk, because there are people out there that want to say, yeah, maybe that is the way that our minds work. But we're pretty sure that that's not the way that our minds work when it comes to thinking and reasoning and then putting those things into language. So if you like this, feel free to subscribe to get the update of the next video, and let me know in the comments if you think that if there's anything you want to talk to me about, or you think that I've made a mistake, or there's a topic that you would like to see addressed, or a question that still remains after this video. And hopefully I'll see you in the next video.